All right, welcome back. So we ended here, and hopefully you were able to answer the survey question. So now we are going to look a little bit at pion mass dependence, because this is where we can really shine compared to the experimentalists, because we're actually able to look at this. So within our EFT, this is where things kind of go awry. The so-called pionless EFT that I showed you previously works very, very well, given that you are at energies that are much, much smaller than the pion mass. And so it's not going to tell us about the pion mass behavior. It won't tell us what happens if we change the pion mass. It's especially not going to tell us what happens if we make the pion mass very large, because then we're not going to be looking at low energies at all. So if we wanted to add pions to the theory, I'm not going to write down a Lagrangian. It can become quite complicated, but pictorially, you can imagine that in the one loop calculation for the scattering amplitude, you might have a diagram that looks like this. I can't draw a dashed line. Okay. Where this dashed line is a pion propagator. So the two nucleons come in, they interact, and then the virtual nucleon exchanges some pion. Well, it's not virtual because, again, this is non-relativistic. So the intermediate nucleons exchange a pion. You can also have pion exchange on the outside as well. But this is just one way where the pion mass dependence for the two nucleon scattering might come in. The problem is, if we're talking about effective field theories, we need to have some small parameter that we can define a power counting for. And when you start introducing more and more scales, so when you start to introduce not only the energy scale that your external particles are scattering at, you have a new scale, which is m pi. This power counting starts to break down. And at least at this point, and in my point of view, there's no power counting for two nucleon systems that works in every channel. So there are lots of different power counting schemes out there. You might hear about Weinberg power counting. There's KSW. Weinberg is kind of, it non-perturbatively sums all of the bubbles and perturbatively adds pions. KSW takes the point of view that we're near unitarity, so we should expand around unitarity. So you're expanding around large scattering lengths. Weinberg is kind of an expansion around small scattering length after resumming a select number of diagrams, etc. The point is, things get messy when you start adding pions. And so here, the EFT formalism doesn't really help us much, which is great for us because we do lattice. So this is a great opportunity for lattice practitioners to contribute to look at the pion mass dependence. So what has been done on the lattice? I'm going to give you just kind of a brief overview of the history of two nucleon calculations. There are broadly two different methods for calculating two nucleon interactions. One, which you've hopefully seen quite a bit in Raoul's lectures, is spectroscopy combined with the Lucier method. And we'll talk a lot about applications of that to nucleon systems here as well. And then another, which is kind of novel for the nuclear physics crowd, is the so-called potential method. So instead of looking at energy levels in a finite box and relating them to scattering phase shifts, the potential method, which we'll talk about in more detail at a later point, calculates a so-called 2-nucleon Nambu beta salpeter wave function, solves the Schrodinger equation to determine a potential. So this is more in tune with what you learn in quantum mechanics. You have a potential that depends on the distance between the two nucleons. It has some hard core in the middle. It's attractive at short distances, and then has a tail at long distances. So they calculate this potential, and from that, they can then get observables like scattering phase shifts, etc. The input to both methods is roughly the same. You calculate energies and potentials using correlation functions. It's just how that information is processed that gives you the different results. And there are pros and cons to both, which again, I'll cover later. Okay, so people have been looking at 2-nucleon scattering for quite some time now. And because of a signal to noise problem, which we'll cover in the next lecture, the easiest calculations to do are at very heavy pion mass. And so a lot of work has been done at the very heavy pion mass around 800 MeV. This is an SU3 symmetric point where you take the up and down quarks to be equal to the mass of the strange quark. This is somewhat of an old plot, but this is from a CalApp paper from 2015, maybe. So I'll say in words what has been done since then. But this is looking at Q cotangent delta. I switched to Q here. We were talking about P before. Oh, it's P here too. Well, hopefully you guys can translate between P and Q. So we have Q cotangent delta versus Q squared, and this is in the 2-nucleon 3s1 scattering channel. So that is the spin triplet channel. And this is where the deuteron lives. So we want to look at our data. You note that there's very little data. We have 2 volumes and only a few points. That's because spectroscopy for nucleons is insanely difficult, and we'll talk about that a lot. So we don't get nearly as much data as you may have seen in, say, scattering phase shifts of meson systems. But this is what we have, and we have a few points near threshold, and so we can use the effective range expansion to kind of interpolate between them, and that's what the blue and pink bands are. This is leading order, this would be to NLO, and then the pink, oh, it's right there. The pink would be to N squared LO, effective range expansion. And then we would want to look for a pole Q cotangent delta equals IQ. And so this is just kind of a zoomed in. So I'm zooming in on this lower region here because that's where IQ is, and that's where we're going to look for an intersection to find a bound state. So I've drawn by hand. This is not in no way precise, but this curve here corresponds to IQ, because remember this, the axis is Q squared. So IQ would be in the negative Q squared region. And then we want to look for intersections between the effective range expansion and for Q cotangent delta and IQ, because that's where we can look for a bound state. The data tells us how to get the effective range expansion, but the data is not going to be exactly where the bound state is unless you're at very, very large volume. And so that's why we need the effective range expansion to extrapolate beyond where we have data. And here, these slides were taken from a talk. I also just showed the other scattering channel, the neutron-neutron scattering channel, for comparison. So we see from my rough sketch that there are 2 crossings if we're looking at the pink band, that's the NNLO ERE, corresponding to these 2 green circles. And that would tell us that there are 2 poles in the scattering amplitude. One is at a much larger value of Q squared than the other one. The other one is very close to threshold. And I should note that we also found energy levels consistent with bound states corresponding to both of these poles using 2 different kinds of operators. And we'll talk about operators quite a bit later on, but just there's some consistency that we see here. Several other groups have done the same thing at roughly the same pion mass, but not always the same ensembles. So NPL QCD and Yamazaki et al. Used similar ensembles. NPL QCD was actually the same ensembles, but only using the operators that corresponded to the deep bound state. And they found evidence for this deep bound state. It's a little tricky to say that they only use the operators corresponding to the deep bound state because they also use operators that gave higher scattering states that were consistent with a scattering phase shift that only gave a single deep bound state. So we'll go into more detail about this later. We're just looking at the overall picture. So 3 collaborations find evidence for a deep bound state. 1 collaboration found evidence for a second shallow bound state. Oh, whoops, I didn't update this. HAL QCD, using their potential method. Here, can I write on this? Yes. HAL QCD. Okay. HAL QCD found no evidence for bound states using their potential method, so no bound states at all. And even more recently, using generalized eigenvalue problem in order to extract the spectrum, which we'll cover in our 3rd lecture. CalLat and collaborators, as well as the Mainz group, found also no evidence for a bound state. So HAL QCD with a potential method plus more recent efforts using Lucier point to the potential that there may not be a bound state. However, there's a caveat. These results are preliminary and need to be checked. Okay. So that is the end of our 2nd video.